In the next part of the lesson, we're going to be talking about factoring. So when we are factoring, we are trying to split a polynomial into all of its prime factors. So if we take a second and think about what that means for numbers. So let's say we have the number 13. 13 is already prime because we can only take 1 times itself. Whereas if we think of 12, 12 has the factors 2 and 6, and then we can break down 6 even further into 2 times 3. So the prime factors of 12 would be 2 times 2 times 3. So we're trying to break a polynomial down into its prime factors, and we're doing that so that we can solve. Now when we start factoring, we still want to use all the rules that we learned from Chapter 4 about factoring quadratics. And we have to remember that when we start factoring, that we always want to check for a greatest common factor first. And our first term should always be positive. So if it's not, that means that we're factoring out a negative. Now we have a couple of different factoring methods. So remember, quadratics, we're using greatest common factor, grouping. When a equals 1, we're trying to find something that multiplies to be the last, adds to be the middle, and then we have the difference of squares for our quadratics. So again, all of that is review from Chapter 4. Okay. Now our new stuff, factoring cubics. Unless we have a greatest common factor, the only way that we know how to factor a cubic equation is by either using the sum or difference of cubes. So what that means is that if we're going to factor a cubic equation, it can only be a binomial, so 2 terms, and both terms have to be perfect cubes. So our problem needs to look something like this. And if that is the case, to help us factor, we have a nice pattern that happens every single time. So a and b are always in the first set, and then it's a squared, a times b, b squared. And we use the acronym SOAP to help us figure out the signs. So the first sign is always the same as the original. So this is a positive, so we have a plus in between. And then the second sign is the opposite, and the last sign is always positive. Okay. So same thing if we have the difference of cubes. It's the same as the original, so this time it's a minus, and then the opposite, so a plus, and then the last one is always positive. And to figure out a and b, we just take the cubed root of the first term, cubed root of the second term. And we always use the positive of that since we have that formula to help figure out how it should fit together. So now before we get into factoring, let's make a list of perfect cubes so we have an idea of what numbers to look for. So 1 cubed is just 1. 2 cubed, so 2 times itself 3 times will be 8. 3 cubed is 27. 4 cubed is going to be, 64. And then 5 cubed is 125. And 6 cubed is 216. And if we want, we can even make our list further. 7 cubed is going to be 343. 8 cubed will be 512. And 9 cubed will be 729. So those are some of the pretty common cubes. Now with variables, for us to create a perfect cube, the power has to be divisible by 3. And we get this from our power rules that we learned in the first section. So really we're looking to rewrite this variable to the third power. So this one, it would just have to be x to the first to the third power. So that means that the cubed root of x cubed is x to the first. So on this next one, to get the inside, so we would take 6 and divide it by 3, which is 2. So x squared cubed would be how we would simplify that to create a perfect cube. So again, I just got that by taking 6 divided by 3. So if I have x to the 9th, our perfect cube would be x cubed, since 3 times 3 is 9. Or if we had x to the 12th, 12 divided by 3 is going to be 4, so we'd have x to the 4th on the inside with the cube on the outside. So the cubed root of x to the 12th is x to the 4th. So that's how we would rewrite those if we need to. All right, so the next set of problems, we just have a bunch of factoring examples using either quadratics, greatest common factor, or the sum or difference of cubes. So we just need to be able to recognize which method we should be using. And again, we always look for greatest common factor, and then we're looking at the highest power to decide what to do next. Okay, so here there's no greatest common factor. We have a squared. So we're trying to find two numbers that multiply to be -4, add to be -3. And then our first term is split as x and x. So this one would have to be a -4 and a +1. Okay? And those are the prime factors. So there's nothing else that we can do to simplify. Next set, our greatest common factor is 4xy squared. Okay, so we're just factoring that out of each term. So 8 divided by 4 is 2. I'm taking away an x, so that'll become an x squared. Taking away 2 y's, so we're not going to have a y term left. 4 divided by 4 is 1. We're taking away an x, so we don't write that. And then we're taking away 2 y's from that one, so 3 minus 2 is 1. So that'll just be a +y. And then there's nothing else that we can do to continue, so then we're done factoring for that problem. All right, next one. So there's no greatest common factor. So if it's factorable, we're going to have to figure out how to split it like a quadratic. So the only thing that 3x squared can split as is 3x and x. And then the only factors of 1 are +1 and +1. So now I just have to check to make sure that this actually factored correctly. So to do that, we multiply the inside and the outside terms, and then that has to add to be this middle term of 5x. So 3x times 1 is 3x. 1 times x is 1x, and if we add, we get 4x, which is not our middle term. So that means that this problem is not factorable, so it is already prime. So that's what we would write, so prime. Problem 6, here we don't have a greatest common factor, but we have a perfect cube for the first term and a perfect cube for the second term. So that means that we're going to use the difference of cubes. So when we factor, this is going to factor into that a minus b, and then a squared plus a times b plus b squared. So now I just need to decide what a and b is. So to get a, we take the cubed root of the first term. So the cubed root of x cubed is x. And again, I'm getting these numbers from that list that we created. So if we have x to the cubed, x to the 1 is our perfect cube. And then 8, so here's my 8. So the cubed root of 8 is 2. So our b value is 2 for this problem. And now I'm just substituting them into this pattern. So we're going to have x minus 2 times the quantity of x squared plus 2x plus 4. And this would be my final factored answer, because there's nothing that multiplies to be 4 and adds to be 2, so we can't continue factoring that problem. All right, we're going to pause there, and we're going to finish these examples up in the next video.